Hey, welcome. This is Brian Ray from Link Labs. I'm here with our CEO, Bob Proctor.
Welcome, everyone.
We're going to start in just another minute. Just give everyone another couple minutes to join. So we'll be right back online. All right, we're going to go ahead and kick things off. I'm Brian Ray. I'm the Chief Technology Officer at Link Labs, and I'm joined here with Bob Proctor, our CEO. And today we're going to be going over asset tracking technologies for the Internet of Things. Dominic, is that showing just fine over there?
Yep.
All right, great. Yeah, so asset tracking technologies and use cases for the Internet of Things. Our agenda today, we're going to kick things off by going through some business cases up front. I know there's a lot of people online that are really interested in some of the technology that we use here at Link Labs and that other people use to track people and things using GPS, Wi-Fi, ultra wideband, and we're gonna dive into those details. But up front, we really want to give an overview of different real IoT business cases that we see every day that are creating a lot of value for customers. And even if you're only interested in the technology, I think it'll be a good grounding for you. And that way, the people that are interested in the business cases get that information up front. Once we go through that, we're going to dive into some technologies that are used to figure out location. And those really break down primarily into two different buckets. And of course, there's other types of technologies as well, but time-based technologies and proximity-based technologies. And then finally, we're going to talk about how Link Labs uses our system and a combination of wireless technologies, including Bluetooth, LoRa, LTE, Cat M1, and Wi-Fi to create a multimodal asset tracking system. So stay tuned for that, and then we'll do a really short live demo, which everyone loves to do on webinars. If you have a question, feel free to throw it over in the live chat. Dominic Marcelino from our team is here answering questions, and if he sees something, he'll interrupt and ask us over here, but he'll be typing madly over there. And if you're watching this as a recording or you have a question that wasn't answered live, jump on over to our forum site at forum.link-labs.com. Post a question. I get those email alerts almost instantly, and I love to answer people's questions on there, as do other people in our community. So that's another great place for your questions. Okay, so just a really quick intro to Link Labs. We've got a lot of people registered for this webinar. Some of you may not be familiar with Link Labs. We're an IoT technology company based in Maryland in the US, and we focus on building and integrating complex industrial enterprise IoT systems. We're very focused on location, and hence this webinar. The technologies we focus on are LTE Cat M1, Symphony Link, which is a type of LoRa technology that we invented here, and Bluetooth Low Energy, which many of you are familiar with, but we'll also get into. And if you're interested in connecting about anything we talk about on the webinar, feel free to reach out to this email address, which I specifically set up for this webinar. Those actually come straight to me, Brian Ray, and I'll either answer you or farm those out to the right people here internally. Okay, so location, that's what we're talking about today. Where is something? Is, in my opinion, really the killer app for the Internet of Things. According to Intel, a white paper I read when I was preparing for this, location is at least a part of greater than 70% of IoT applications. And you may be like, wait, that doesn't make any sense, 70%? And that's just a part of it. And if you think about the role location plays in almost every vertical solution, you can start to see why it's so prevalent. If you're monitoring equipment, it's actually important to know where the equipment is. If you're tracking people and vehicles, it's obvious why location is important. If you're a Nest thermostat, knowing the weather, knowing the humidity in the location where you are is important, and that is calculated from location. And how that's done with various technologies we'll get into at the end, things like GPS, ultra-wideband, Wi-Fi, Bluetooth, even simple IP address databases or Wi-Fi fingerprinting databases. All of these various technologies can be used and mashed up to add the location context, which is so important in the Internet of Things. Okay, we're going to talk about use cases. We're going to talk about business value and location. And this is the ontology that I love to look at when I'm thinking about different IoT business cases. And this comes from Michael Porter's article in Harvard Business Review from a couple of years ago, where he said there's really 4 different layers of capability that Internet of Things applications can create, and each one is increasingly more valuable to organizations. The first one, monitoring. This is simple. This is getting information, and in location, it's really where is it? And if you're monitoring things, this could be the location of my fleet. Where is Bob? Where is the material I'm looking for that job? And those can be tremendously valuable questions to answer. But if you look up the stack, you can start to do even more powerful things with them, like control. This could be like change the settings of a machine based on the weather in a certain location, stop a vehicle as it's leaving campus. Being able to send controls and commands back down to connected controllers is really powerful. Above that, optimization. This is taking the inputs from the sensors, from location, making some optimization decision through an algorithm to enhance their performance. So connected tractor might be using its location and an image analysis to vary the level of fertilizer as it's driving around the field. We might send driving directions to a delivery driver to give them the fastest route based on their location. Or I might be routing somebody to a free parking space. These are all examples of optimization, where it takes a fairly complex data set and algorithm to deliver that optimum experience. And then really kind of the holy grail of Internet of Things is autonomy, which is where the Internet of Things sensor server decision loop is closed and commands are sent back down automatically without a human in the loop. Like, we have detected a shipment is delayed, therefore we're going to automatically reship a replacement without a human having to make that decision. We're going to order more parts because we've detected an increase in usage based on our location tracking. We're going to change the staffing in a certain work center tomorrow because we've noticed that there's a lot of work in progress that's stacked up. These are all examples of autonomy that we've seen. And then this is an IoT stack diagram that I really like, which shows both the physical product, the hardware and embedded software, the connectivity, and then the server side. And it's important to note that location doesn't just happen in the hardware. It's not all just a GPS chip. Things like Wi-Fi fingerprinting or network, cellular-based connections, these often involve the network layer and then database layers to bring IoT location together. Okay, so now we're going to dive into some use cases, which I think will help you understand how we see value being created in IoT and location. The first use case we've selected here, Bob, is smart manufacturing. So this is a manufacturer that we're working with that had previously been tracking work in progress or WIP components through a large multi-step manufacturing test and rework center by people scanning barcodes on sheets of paper as it moves from one station to the next. And the problem that they were facing is that sometimes parts would be delayed because they would fail to move to the next station. They would have to physically dispatch a person to go manually track down, hey, where is this thing? So we worked with them to implement an indoor asset tracking system where the work in progress components are tagged, and then a very lightweight Bluetooth-based indoor location tracking system is installed throughout the plant. And it allows them, in the early days, just to see a dashboard of where is everything, and that created tremendous value. But as that product and that solution matures, they're looking for ways to automate the process of alerting and telling people where there's issues.
Yeah, let me jump in here, as Bob. So if you're familiar with Lean Six Sigma, you're in a production manufacturing environment, you're thinking about optimization and elimination of waste. Waste can come in many forms in a manufacturing environment, from unnecessary moves, finding equipment, finding tools. So something as simple as I've got a tool cart that services a specific workstation. I need to know that all the tools are on that cart, and that something was not left behind. These are all examples. So this type of tracking and indoor tracking capability, we'll talk about with AirFinder at the end of the webinar, how this works at a very low cost and low price point, really opens up the possibility of adding a technology service layer into a traditional Lean Six Sigma operation to provide much richer information flow and optimization capability in a production environment. It's really quite compelling.
Thanks, Bob. Another use case I've got here, I struggle to come up with a name for this, but I call it commercial consumable management. So these are a class of companies that supply various things, whether it's air gas, lube oil, paper, and other things into an enterprise or an industrial environment where they go around and they deliver it, based on some cycle. And it's obvious to them that there's tremendous savings to be generated by optimizing the delivery and inventory that's held at customers based on usage. The problem being that there is no way to know how much is being used in different locations and what is in inventory, except previously a very manual process. So we've implemented really a full life cycle tracking and monitoring system where these units are tracked inside a fulfillment center as they're moved in different bins of inventory. Then they're tracked as they're put on delivery vehicles. There's a difference that's calculated when material is pulled off the truck. It disappears from that sensor, and so it's inferred to have been delivered at that location. And now we're layering in usage sensors that are connected back via cellular and LTE-M that offer information about how the product is being used. So really powerful system for a lot of industries out there, trucks that you see driving around every day delivering different materials.
Yeah, the analogy here would be if you're in the consumer packaged goods industry, point of sale information is transmitted back to you, and you can use that information to optimize distribution as well as production based on receiving that demand signal almost in real time. Mm-hmm. But in a commercial environment with commercial consumables, that demand signal doesn't exist, so the optimization really hasn't happened on both the distribution and supply chain side. So there's an enormous opportunity with IoT and location coupled with sensing to now understand both the demand signal and where everything is in both my distribution and supply chain and drive a lot of value that way.
Another use case, I just call this logistics. We have several customers in this space. The example I pulled out here is we have a manufacturer who is using materials in their factory that are produced by a network of suppliers across the country. And they have to plan work in their factory based on the availability of these different, I don't want to call them raw materials, but component parts, which are brought in by truck. And they face a lot of problems with planned versus actual deliveries, meaning stuff was supposed to arrive on Monday but doesn't arrive on Tuesday. It can cause serious delays and downtimes on very complicated manufacturing lines. So by implementing a multi-stage tracking system where pallets of goods are tracked with cellular when they're on the trailer, and then those trailers and pallets are tracked using proximity sensors in the yard, and then additionally inside the plant in some cases, they're able to eliminate a lot of these inefficiencies and improve the throughput and speed at which they're able to manufacture.
Yeah, let me just riff on this a little bit as well. If a tractor trailer is approaching a receiving gate, that may have a data logging device on it in today's systems, but once it's inside a facility, you really don't know where it went within receiving or warehousing. And so the ability to seamlessly transition from in transit to inside my facility without having the need for some human-driven process and intervention, be it tagging things, barcode scanning things, and transitioning across systems. Eliminating that step often means that component parts that you may know they're on your facility somewhere, but you now lost track of where they are, can cause huge disruptions into production. So this seamless ability to take the human out of the equation in these transition points between outdoors and indoors is also a very valuable use case.
We had a good question from the stream here about how to explain the different parts that were used to implement one of the use cases. Maybe we could talk about the manufacturing use case or one of the earlier ones.
Yeah, it may be worth waiting until the end where I actually draw some diagrams of those different pieces. But I'll try to touch back to the different use cases when I show that. So stay tuned on that. I actually drew some of these out, which I think may be helpful.
Great.
Construction management. This is a space that we've seen quite a lot of interest in. And here there's multiple different ways where value is created. An example I've given here, a general contractor may be using prefab assemblies that are built off-site and then are brought to the job site and then installed. The problem being, if the site is ready to receive that prefab, when it gets there, everything is great, but oftentimes it's brought early and it's stashed somewhere, and being able to find that material when it's needed is actually a big problem. It can create a lot of waste. I've actually heard of large general contractors spending hundreds of thousands or millions of dollars recreating things that they lost in weeds that grew up around stuff that was delivered to a site. In addition to that specific use case, we see a lot of interest in tracking subcontractors, personnel, and materials more generally throughout the site, so that you can know when subcontractors are working on different floors. You can track equipment utilization. You can monitor worker safety if there's a problem, a fire, an emergency, like who's left on site. And also from a compliance standpoint, who was on the site yesterday when something went missing, or just being able to audit different bills. Like we got billed for drywall work on Tuesday. Were there any drywall workers there on Tuesday? That kind of thing. Those are all use cases that we've definitely seen. And the system, that we'll talk about, being able to use a very lightweight infrastructure in a very temporary way using Bluetooth, lends itself well to construction.
Yeah, no, I would just add is another perfect example of construction is like a production environment where you have people, materials, and tools that need to be on the right area of the construction at the right time. If you have any excess materials, people or tools showing up in that area, then people are stumbling over it. The whole operation gets much more inefficient. So getting the right groups of assets, people and materials and tools into the right space at the right time and managing that flow and creating transparency around that flow of materials and people is really valuable in a construction setting.
The last use case example we have here, service delivery. The example we have is a telecom company that drives around in vans and visits businesses and residences to install equipment. Sometimes they leave relatively expensive equipment, signal analyzers, cable testers, and other things behind on job sites. And it's actually relatively expensive for those companies to replace them. By implementing a lightweight Bluetooth-based asset tagging system that essentially alerts when a van leaves a site without that equipment on board and creates an exception, is generating pretty significant value because they're getting alerted when either raw material or instruments are left on site. It has additional benefit that now you have a mechanism to track vehicle and personnel as well. But it's a nice use case because it's very laser focused on a specific problem, and then it can grow from there.
Yep. Yeah. Any company that has a service fleet, this is sort of a no-brainer.
Some other use cases that we're involved in that I'm not going to dive into, but just want to talk about it at a high level. Healthcare real-time location. This is very prevalent. This is tracking material, people, assets in healthcare and hospitals. Vehicle and key tracking for large dealers and brokers. Some large auction sites, they have tens of thousands of vehicles, and tracking the keys and the vehicles turns out to be an expensive problem when they go missing. We are also involved in tracking ground service equipment at airports and monitoring personnel, mines, prisons, and other facilities.
Yeah, on the personnel bit, I just, we're seeing more and more interest in commercial real estate and understanding utilization of the space assets just by having a lightweight way of tracking how often are people using large conference rooms, small conference rooms, desk space, those types of things. So you can start to take an expensive cost of commercial real estate and understand its effective utilization across your employee population.
So what are the technology implications from the use cases that we've just given is a good launching point. And I think one of the first conclusions is that in many cases, location is multimodal, meaning it's no longer okay just to say, what's the GPS point on the map, or what is the closest Bluetooth access point? We see customers combining different location capabilities with Wi-Fi plus GPS plus cellular plus Bluetooth in different ways to give them a seamless indoor and outdoor capability that meets the cost targets, the battery life targets, and other pieces of the system that they're looking to put together. In terms of cost, the biggest drivers absolutely are the tags. If you're trying to track a lot of things, you want that tag cost to be as low as possible. Many of these tags are active emitters. They have a limited battery life, so managing that cost, and also the size, form factor. You can't put a giant, Wi-Fi brick tag on a tiny instrument. It's never going to work. Infrastructure, some of the technologies we're going to talk about require a lot of expensive infrastructure and surveying, whereas others require less. And then finally, connectivity. It's the Internet of Things. That data has to get somewhere for it to be aggregated and value created. If that's Ethernet, that's great. If it's Wi-Fi, that can create problems. If it's cellular, you have to pay the network operator. And that's where cellular data and the management of it become very important. And that's where we're very focused as a company in terms of reducing the overhead and the payload sizes associated with sending this data up so that you can actually make use of some of these very low cost IoT cellular data plans that are out there. You have to be really creative in how you architect the system.
Yeah, Bob, let me just jump in on the cellular piece, because I think it's lost on many folks that call it order of magnitude $1 a megabyte a month. People say, hey, that's $1 a month. That's very inexpensive. But if you compare $1 a megabyte a month to a consumer cell phone plan, the order of magnitude there would be about $1 100 megabytes a month. So you're really talking about something that, from an information flow perspective, measured in megabytes, is 100 times more expensive. So if you're really sending data that is not really valuable as information, you're racking up a pretty significant phone bill for a very low ROI. So managing the data piece is a very, very critical part of making these asset tracking technologies that use mobile network operators have a high ROI.
Okay, so now I'm going to jump into some of the technologies at play here, and I am going to mostly address this at a pretty high level. A lot of the information here, if you want to really dive in deep, there's textbooks, there's YouTube videos. This is not meant to be a deep dive on anything, just really skimming the surface of different technologies to give a generalist a better view of how to architect some of these systems. So the first general quote technology of calculating location is time, and that's because time is distance. You know the speed of light, or you know the speed of sound, and if you can measure how long it takes signals to propagate from one place to another, you can use that to calculate time. Now, that being said, it's a lot harder than it sounds. For instance, it's almost impossible to calculate a one-way single distance from point A to point B, because you have to somehow synchronize the clock so that B knows when A transmitted. But unless you're running hyper expensive rubidium atomic clocks on both of these endpoints, you're never going to be able to do that. So you almost never see a one-way time of flight type system. The second example here I have here, round trip ranging. This is actually becoming more and more common. Up until recently, though, the amount of processing it took on both A and B here to make this happen, required too much power for most IoT devices. But now there's ASICs on the market. There's chips that are starting to do this, and it's making for some interesting technologies. But this is essentially, A sends a message, B receives it, and then turns around and transmits back in some deterministic way, so that A can say, okay, it took 2 seconds for my message to go there and back, therefore the distance might be 1 second, and therefore I know that how far B is away from me. And the final way, which is much, much more common in most of the systems that use time, is called time difference of arrival, where you compare the difference between receiving a signal at multiple different reception points. And the nice thing about this is it requires no synchronization on the tag itself. So in this example here, the tag just sends a message out and it's received by 3 different receivers. And each receiver then can go back and behind the scenes, hey, B can say, hey, I received this at this time. A says, oh, I received it at that time. And what you get is hyperbolic solutions, which on this slide you can see that the line of position between C and A's time difference for point X is this hyperbola, and between B and A is this hyperbola. And these 2 hyperbolas, they actually intersect in 2 different spots. I'm just showing one here. So for a 3-pointed TDOA solution, you actually have an ambiguity that you need to resolve, which is why you often need 4 receivers in a TDOA system. And if this is a TDOA system like ultra wideband, you have to have 4 different receivers all wired together to receive every single transmission, which is why TDOA systems are often considered to be the gold standard of indoor accuracy, but they can require pretty significant infrastructure investment, which might not create the ROI you're looking for, which is one of the reasons that we see customers shying away from using it. It also requires a lot of calibration. And all of those receivers, they have to be slinging time synchronization back and forth, because A, B, and C in this case all have to have the exact same time down to a couple of nanoseconds or less in order to make this work. And they do that by using both their network and by sending packets over the air, these timing packets all the time, to make sure that everybody is synced up together. But this is how some of the newer Wi-Fi based positioning systems work. This is how ultra wideband works, and then there's a lot of proprietary based, microwave ranging systems that are used in different settings as well. GPS. Almost everyone has heard of GPS, Global Positioning System. GPS constellation is an American military technology. There's also a Russian technology called GLONASS. They're very similar, but these are satellite constellations that are extremely technologically sophisticated and are operated. There's dozens of Air Force personnel sitting in Colorado right now comparing all ephemeris data and timing data and looking at ionospheric conditions and flying these satellites to make this system work. So it's certainly not an automatic thing. How GPS works is phenomenally complicated. I could do 10 hours on how GPS works, but to do it in a couple minutes is tough. But at its most simple, you can think about GPS as a 2-step process. The satellites are all sending out data, which is called ephemeris and almanac data. So almanac data is where are the satellites generally right now? Which ones are online? Which ones are offline? What's their orbital plane? What's their location? And that information is sent out over a series of many minutes, which is why if you've ever cold started the GPS, it can take seemingly forever for it to work, because it's actually just listening to the almanac come down, because it can't do anything until it receives an almanac. And then ephemeris data is on a space vehicle or satellite by satellite basis, corrections to the time constant for that specific satellite. So it's saying, is it running slow? Is it running fast? Is it out of its orbital plane, etc. And so ephemeris and almanac is kind of the starting point for your GPS receiver to then start receiving PN codes. And a PN code stands for pseudo-random noise. All the satellites are all transmitting a spread spectrum signal on the exact same frequency at the exact same time. And your little GPS receiver is looking for a code from the satellite. So here's the satellite sending this, 1s and 0 code, which is in reality spread over a megahertz. And your receiver is looking for that replica code. But in reality, by the time it is received on the receiver, it's shifted in time. And so your receiver starts slowly moving the code through time until it gets a match or a correlation. And it says, okay, I hear satellite number 1, and I know that satellite number 1 sent this message X time ago. Well, when it hears the first message, actually doesn't know when it was sent. And so for the first, part of a GPS fix, the GPS receiver is actually just trying to figure out what time it is, because once it can calculate the time by measuring this difference from multiple satellites, then it can start to actually figure out where it is by time stamping all of these signals that are coming down once a second. So you get 3 satellites is the minimum for a single position, but generally requires 4 or more to give a position, velocity, time measurement. It works very well, but it has some limitations. GPS has a 6-meter best case clear sky accuracy, and that is limited by many factors. Just the effects of general relativity or the distortion of space-time due to gravity of your receiver on Earth versus the satellite in the sky is responsible for almost 40 meters of error, which the satellites actually correct out in their ephemeris data. There's the effects of special relativity, and then the effects that are harder to calibrate of the ionic sphere. As those waves are distorted as they go through the atmosphere, their length changes, and it's very difficult to calibrate that out. And so that's kind of the root of this 6-meter best case accuracy. But in reality, that's very good, because that means that all 30 plus of those satellites are all locked in time together, and they're all being managed very accurately to make that happen. GPS is also very power hungry. Think about all of the math that I said has to be done. You're correlating across a megahertz of bandwidth against 30 different targets all simultaneously. The fact that that can even be done in a tiny chip for 30 milliamps is a miracle. It used to take racks and racks of equipment in the 60s to calculate a GPS position, but it's not a power efficient technology. So turning on a GPS in an IoT device that has batteries is a very expensive operation, and one that has a real impact on battery life. Also, the antenna for your GPS receiver has to have an almost clear view of the sky, meaning you can't put a small GPS receiver in a box, in a pallet, in a truck, and expect to be able to hear the GPS satellites. The signal that's being sent from them is just too weak to be detected. And then finally, in cities and places where often you want to track things, multipath or the reflection of signals off of buildings can create a tremendous amount of error. It's not uncommon to have a GPS solution in a city like New York be greater than a kilometer off from reality because of this effect. So that's why things like phones, they often use Wi-Fi fingerprinting in addition to GPS to actually figure out where you are, because otherwise it would be hopeless. So Wi-Fi fingerprinting, there's really kind of 2 different ways to think about this, indoor and outdoor. Here's our office at Link Labs. This is the Wiggle database. This is an open source tool, but you can see there's the Link Labs network right there. And so if I was to ask Wiggle, hey, I see this network, where am I? It would say, oh, you're right here, which isn't that far away. And it can do cool things like trilaterate and other things. Google has a great Wi-Fi database. There's Skyhook and others that do this on the outdoor side. So you can put a Wi-Fi receiver in that box on the pallet in the truck, and you can still generally hear those networks because they're much louder. And then you can send that information out using something like LTE, and you get back on the database side your location. If you're using Wi-Fi for indoor location, just from a fingerprinting or RSI perspective, it can be a little rough. Here's a Cisco tool that I screenshotted that helps you set up access points to do RSSI-based locations. So it's a little rough, especially if you're not using the TDOA features like we talked about. But it is certainly possible to at least give you a rough location. And now the final or alternative type of technology that I want to talk about is proximity. Proximity is very simple. It is based on received signal strength. So really, who is my loudest neighbor? Who is the closest to me is really the question that these systems are asking. And this sounds as simple as it is. And the reason that it's used in IoT systems is because it's very inexpensive to implement. Instead of having to create very expensive TDOA infrastructure, you can now put very low-cost beacons out, use tags as beacons, et cetera, to create location using proximity. So in this example, I've got a tag. It's beaconing. If it's using Bluetooth, it's advertising maybe every 30 milliseconds, maybe every 100 milliseconds. And all of these different receivers are hearing that tag's advertisement, and then they're all sending that raw data back up to the cloud, where the cloud says, oh, based on that mesh of signal strengths, the tag is here. The downside of this architecture, though, is that all that raw data from all of those readers needs to constantly flow up to a server in order to make that determination. So what we've started doing here at Link Labs with our AirFinder system is reversing that. So now the tag listens, and the reference points, which can be much simpler. Now they're not connected to the internet. They're very simple. They are basically just tags themselves. Bluetooth tags. They're beaconing. The tag is sleeping. It wakes up, does a scan. It calculates its own position, and then it sends that position to some access point, says, oh, I'm right here, and then it goes back to sleep. So this allows us to really save on the amount of data we're transmitting. It improves the accuracy because you can put many, many more low-cost reference points in a room than you could with other technologies, and it lowers the latency because the tag sees the location change instantly. It can report that back up, and you can know in milliseconds that you've changed. With this other technology or this other architecture, it can take a little bit more time as that raw data flows up for the system to decide where the tag is. I've got this chart here that I like from ResearchGate that shows all of the different technologies we've talked about. One of the things we didn't talk too much about is cellular-based or cell-wide fingerprinting. This is pretty commonly used actually, but it doesn't give great resolution. It's the cellular user equipment is reporting all of the cell towers it sees. So much like we were doing with Wi-Fi fingerprinting, it's doing it on a larger scale. And generally, you're getting about 1 kilometer of accuracy, which, believe it or not, for some applications is fine. And then as you drive down, we've got ultra wideband, which I said is really the gold standard in terms of accuracy. And then you have some of these hybrid methods using RF, infrared, ultrasonic, et cetera. Okay, so this is Dominic. This is the some of the diagrams that I was mentioning earlier that I was hoping to show people. So here's a typical customer scenario where we want to be able to track a low-cost tag indoors and outdoors. So this tag is nothing more than a Bluetooth transceiver. And what it does is when it's indoors, it wakes up and it listens to any of the Bluetooth references around it. It calculates where it is based on those references, and then it connects up to a Bluetooth receiver in what we call a Bluetooth access point. And it says, hey, I'm in location A. And then that thing is connected via low power wide area network, usually our Symphony Link technology, over the air back to a centrally located gateway, and then that flows up to the cloud. Now, when this tag gets put on a truck, there's a Bluetooth receiver that it can connect to and say, hey, I hear you, I'm near you. And this guy knows its position from GPS and then can send that data back out via LTE-M. So as it's driving around, you're getting the dot on the map of this guy, and then when it goes inside, it transitions over to using the proximity-based BLE reference. So this is a relatively complicated system, but it's very inexpensive to implement because the tags themselves are nothing more than simple beacons. The reference points also simple beacons. You don't need too many access points in an area to pick up those transmissions. They generally cover, hundreds of square meters. And then, the truck, if you can put in your own infrastructure in the truck, it's a great way to connect up. But that's sometimes not possible. A lot of over-the-road trucking scenarios, you're not able to put any of your own infrastructure in the truck. And so that necessitates this other alternative architecture where the tag itself has the ability to talk out to the wider network. But this has the advantage of simplifying your infrastructure everywhere else. So kind of at the expense of a slightly more expensive tag, now I'm getting very, very lightweight infrastructure everywhere else. So this tag has an LTE-M radio in it to send data in and out. Maybe it has a Wi-Fi receiver, maybe not, and it definitely has a Bluetooth receiver. So when it's inside the factory, it can read out the Bluetooth reference points and send those out via LTE. And when it's in the truck, as it's driving around, it can ask that the LTE only location be used. Remember, you're getting about 500 meters or kilometers as things driving around. Or if the truck is parked in a parking lot or driving down the road by a Wi-Fi access point, the tag can grab that and report that out to further refine the accuracy there. So we've seen customers go both ways.
Yeah, let me just jump in for a second. This is a classic example of where we're doing indoor-outdoor with a very low price point that also is very data efficient. The key here is the reference point architecture. This is flowing through something where you know where it is indoors. You've got the ability with that reference point to understand indoors. That's the BLE reference to the BLE receiver. When you're on the truck, you're looking at just a Wi-Fi receiver that's starting to tell you, I understand I'm coupling that to a database in the back end, and that's always being transmitted out via LTE-M. But because the tag is figuring out where it only is transmitting through LTE-M when it's moving. And that's what makes it very data efficient. That's what makes these this architecture very, very cost effective. It's much, much lower cost to operate than something where you're constantly transmitting information and figuring out where it is in the cloud and sending information back up and down on a steady basis. So it's a very powerful architecture.
Yeah, I agree. Just to really drive the point home about our AirFinder system, here is an example of a Bluetooth key, which is reading out these Bluetooth reference points that are nearby, calculating the closest one, sending that data back to the Bluetooth access point, which is then relaying that data either via SymphonyLink, our LP-WAN technology, or LTE to the back end, where our customers, generally they pull data from our location API, but we also have a nice asset tracking front end that they can use, for their use cases. I'm going to just do a little demo here in the office, kind of showing the power of this beacon-based and tag-based location system. So, what we might have is you might have 2 rooms, and you would have a reference point, say, on every desk. And the nice thing is these are just very, very inexpensive Bluetooth beacons. Very simple, very long battery life. And then the tag itself is also Bluetooth, but it's a Bluetooth receiver. So it's looking at what Bluetooth devices are on the air and calculating through an algorithm running on the chip its location. And then it connects to the Bluetooth infrastructure and then reports that back to the back end. So if I go over to my... So here's our office. We overlaid a floor plan, so this is just a simple overlay. We've got Dominic here with a tag. So Dominic, do you want to walk the tag out of here and show it move? So you can kind of get a sense of the latency as he, we're actually in this conference room here. Okay, so go ahead.
You're just moving across the conference room.
So go on out. He's walking to
the far end of the conference room.
Actually, he left, so he's now over here. All right, now come on back. All right. So you can see, this is, this was implemented with, less than $100 worth of equipment, and we're getting room level and desk level accuracy in our office, relatively well. Let's see if it moves back to home base. There we go. Okay, that's all the presentation material we have. Dominic, I know you were stepped out for a second, but do you have any questions? Sorry, we have some ambulances going by here. Do you have any questions from the chat that we should address?
Yeah, a couple. So Joe Madden from Mobile Experts was asking,
hey Joe,
if our customers were generally upgrading from RFID systems, or we were seeing more white space installations with what we're doing right now.
I would say in healthcare, we're seeing a lot of what I call overlay, which is customers that are actually already have extensive RTLS deployments, but it's not working for them from either a tag cost perspective, the interface is too complicated, it's too expensive. And we're often coming into these facilities and solving a specific problem, like OR supply chain management, operating room supply chain management, where we install kind of in a subset. Certainly almost every large customer we've talked to has either at one point tried to implement RFID or looked at other stuff across the waterfront. But it's hard to generalize. Bob, do you have any thoughts on that?
No, if I was forced into a choice, I'd say we're seeing more white space opportunity because the cost of the tag and the infrastructure with this type of technology is an order of magnitude less to install and operate, generally speaking. So just given that you can now lower the price point on a high accuracy tracking capability is opening people's eyes up to lots of use cases that just weren't economic before become economic now.
Yeah, one thing that I didn't talk about in the presentation is passive RFID. My theory about passive RFID, and just to let everyone know what that is very, very low cost tags with no battery that get excited by fixed infrastructure, and then they kind of report back their identification number. This is how, when you try to steal something from Home Depot, that's how the door beeps, the library book type tags. I feel like every use case where passive RFID could work has already been done, and there was a lot of excitement, 10 years ago around passive RFID. And as that died away, there was still all these use cases where it just wouldn't work. Like you just can't put a passive reader in an 18-wheeler and expect it to be able to penetrate, all these boxes. So there's a lot of use case waterfront left over for what we're talking about here, which is more active RFID. And it's really made possible by the, as Bluetooth becomes less expensive and as these, very power efficient and cost effective cellular networks become available as well. Dominic?
Another question that we had was, I guess getting into the role that the location in IoT plays with LPWAN. So basically the combination of those two things. Specifically, you could do location with cellular or with Wi-Fi, but specifically how that integration with the low power wide area networks you've seen.
Yeah, obviously Link Labs we're big in low power wide area network technology, but where we see it is it's a local area data backbone. It's not a technology that can itself be used very well to calculate location. We're looking at tags that receive Bluetooth on one end and transmit out with LoRa on the other end, for example. But it's not the type of technology that can really be used effectively to pinpoint location from a radio perspective, just because it's too narrow band.
I would just add to that on the way I think about it is cellular connectivity, as mentioned earlier, even at $1 a megabyte a month, can be quite expensive. In a fixed area, a building, campus, those types of things, deploying an LPWAN service layer is really just a further cost optimization of a deployment. You don't have to backhaul at that point through that expensive data pipe.
Yeah, so we've got a bunch of questions from Fabricio and several others related to the prices that we've seen on tag, basically the costs that we're seeing for the different elements of this system, and kind of where you see the I guess maybe your thoughts on costs in general, because it's not just about tags.
Yeah. So I mean, certainly Bluetooth tags are really far down the cost curve. They're manufactured in China. I've seen tags as cheap as $2, kind of up to the $10 to $15 range, depending on how it's packaged, what size battery it has, how many of them you're buying. Other types of tags, ultra wideband is a technology where I think the tags are kind of artificially cheap because the vendors there are selling you kind of both ends of the system, and the infrastructure is very expensive. But those tags generally can be in the $5 to $10 range. Wi-Fi based tags generally are more expensive. The RTLS tags for systems like a WarePoint, AeroScout and others, those generally are in the $40 to $60 range. But it's really important to think about not just the specific cost of one particular element of the system, but the whole thing. How much does the infrastructure cost? How much are you paying in connectivity? How much does it cost to install, maintain, et cetera? So the cost model of these systems can get complex.
Yeah, no, I would agree that generally speaking, Bluetooth is going to be mass customized, so you can get every form factor, every battery size you want. It's down the cost curve. It's ubiquitous. So on the tag end of things, Bluetooth is likely to dominate in our view. Then the question is, how do you build the intermediate connectivity layers most cost effectively? LPWAN and CAT-M, LTM technologies are certainly the best for that. They're the lowest cost from an infrastructure perspective, and they work very well together. Another thing I'd note, we've talked all about asset tracking here, but this general architecture can be used for asset monitoring as well. We didn't emphasize that as much as we might have. You can not only use a Bluetooth tag to know where something is, but that can have a temperature monitor on it. So if you're doing cold chain monitoring, you can understand temperature. Or if you're in an industrial environment and you deploy this service layer for asset tracking, like we talked about in a factory use case, well, now I have a service layer that I can put Bluetooth enabled vibration, temperature, environmental monitors on equipment, and now I can do predictive maintenance off of that same infrastructure. So it's a very powerful architecture. And again, the infrastructure at the facility level is generally significantly lower in cost. The tags are significantly lower in cost. And then there's architectural flexibility on how you backhaul that via LPWAN or network operator. So it's a pretty compelling architecture overall.
I know you covered this a little bit, Brian, but there were a couple questions related to kind of combining GPS and other assistance technologies in order to kind of refine the way that we would locate things that are outside. Do you have any kind of additional thoughts on?
Yeah, I mean, the ways to aid GPS, I mean, that's a really sophisticated field. There's differential GPS, which relies on sighted receivers transmitting correction information around. You can do network assisted GPS, where the carrier networks help the GPS receiver figure out what time it is faster so they can start measuring position sooner. But yeah, it's a pretty complicated space, but certainly a well developed one. I mean, GPS can be so accurate in many cases used for surveying, down to centimeters.
There's also a question about, I guess, Bluetooth 5 and the role that you see potentially Bluetooth mesh built on.
Yeah, I did a whole other webinar on Bluetooth at one point. Bluetooth 5 is not, I would say, a revolution. It's an evolution. I don't think it's so different. It's increasing performance, increasing range. There's more channels, but fundamentally, it's still, especially on the BLE side, it's still a high-speed, short-range data exchange connection system. So they're making improvements to it, different chipsets, but not a big game changer from my perspective.
I would also just offer, outside of the Bluetooth question, but generally speaking, there are a lot of techniques that you can apply to make these also more power and data efficient, which improves the ROI. And they're pretty straightforward, commonly used. Accelerometers can tell you if something's moving or not, and whether or not you fire up the radios and burn data and power. Geofencing can be used to determine if you're using a GPS device or activated or not. So there's a lot of techniques to drive the power efficiency of these systems once you get into the specifics of your use case that can really extend the operational life and lower the overall cost.
All right, I'm going to share my screen here one more time. If you have any follow-up questions, please reach out to us at webinar@link-labs.com or post it on the forum site here. We're happy to answer those questions that you post. And thanks a lot for a great webinar.
Thank you.
All right.